Hello. Well, looks like we can get started. Welcome back, everyone. This is going to be the last instructional week of the entire semester, so that's kind of exciting. And I dropped the ball. I was intending on a quiz 9, but I just completely forgot to post it. So we're going to make quiz 8 our official last quiz. It'd be kind of rough to try to just squeeze one right in the middle right here. But aside from that, the announcements are, as usual, just kind of scattered across the Moodle website. I gave 4 exams this week. I'm questioning the wisdom in that, but this is the third exam that I gave. So that means I'll probably be grading this one on Saturday, potentially concluding it on Sunday as well. So I'll have those all graded up and return to you in the normal kind of way. But this is also a big transition week. Next week is closed week, which means we're not going to do any kind of new material. We're going to be reviewing. But all at the same time, I have a problem with my schedule on Tuesday, April 9th, 29th specifically. My spouse has a procedure called left cubital tunnel release ulnar nerve decompression, nerve transportation of interest, if necessary. What that is a kind of carpal tunnel. There's a nerve here that can get a little caught due to inflammation of some kind, and it can make your left part of your hand and your arm go completely numb. Interesting feeling. We've got to get this done before neuropathy sets in, and this is the surgeon's schedule. Sorry about that, folks. That is a spectacularly terrible timing. But when it comes to surgeries, we just have to stick with the surgeon himself. It's a quick one. They just do a little slice here, clean up the area that's causing the compression, and then move the nerve if necessary. It takes about 45 minutes, but I have to be the one to drive because you do get anesthetized for that. Because of that really terrible timing, losing a whole entire day on closed week, I'll make it up to the class by posting the real final exam from last semester, fall 2024. That way that can bolster the studying, that kind of stuff. I'm also going to hold a special office hours review session on Friday, possibly not the most ideal time for folks, but I'll be available from 1 p.m. to 2 p.m. as well. Also, we will have classes normal on Thursday. I'll be in here. I'll have down below, probably posted right around here, the final exam, the real one from fall 2024, maybe an extra one if you want another one just for extra practice. And then the similar kind of documents like you're seeing for exams 1, 2, and 3. I'll post 3 different extra versions just for extra problems. So sorry about that timing, folks. I realize that's really terrible. I've had to cancel also the office hours in the tutoring room at that same time, but we'll get through it one way or another. Let me just get this back to where it was. Yeah, go ahead. That's correct. Yeah. We're going to get pretty far into these notes today, possibly finishing it entirely. Whichever problem we end on is the scope of the final exam. But any problem on here that's beyond what we actually covered on the class, I'll put in the full solutions. And the very last problems, if we don't get to them, could form an extra credit quiz or extra credit problem on the real final exam. So the last problems on the back of there are application problems. They're not too bad, but if you have the extra time and energy to go beyond, study those problems and the solution I post, the extra credit will be substantial on the final exam. Final exam scores can't exceed 100%, but it's kind of like a problem swap. If there's one problem on the final exam that you felt, I'm not too sure how this goes, I just forgot, the extra credit question is one you can get into to kind of replace that question as well. Yeah. That is a really good question. I'm going to post the fall 2024 final exam. So let's just take a look at it to get a good idea. I try to keep all my exams about the same length. Sometimes the problems change here and there, so it's not always the same exact problems. So I'll post a couple versions so you can see some variety. But let's go back in time here to fall 2024.
In this classroom still, right?
Yeah, it's an odd time, Friday from 10 a.m. to noon. Some people mentioned they'd rather take it earlier, and if that's you, that can be arranged. Just let me know where's these courses. There we go. So this was fall 2024. And in fall 2024, here is the final exam with the solutions. Looks like this one was 11 questions altogether with the extra credit question at the end. Our extra credit question is not necessarily going to be this one, but same kind of idea. So this was a problem the math department threw on here. I didn't like this question. A lot of people absolutely hated it last semester. I'm not going to expect to ask another one like this. Because Math 1160 is considered a general education requirement type of class, the State Board of Education forces a problem like this one onto our exam. Our exam problem that gets forced in is a routine problem, not something like this that doesn't even feel like it's covered in calculus. This is an intermediate algebra kind of problem, plotting graphs and that kind of stuff. This problem is a little bit more along the right lines, estimating areas. This one here was an application problem. It looks like it deals with finding antiderivatives and that kind of work. And this is a little bit more similar to the work that we covered in our class. This is an optimization problem. Going backwards, looks like we're doing concavity. This is starting to look like exam 3, essentially. This was exponential growth. Then looks like a random set of compute some derivatives. This one here was about dealing with an application problem. This is an interpretation of a derivative, where if that's a function and you differentiate it, then to interpret the meaning, it's actually really tricky. This is a hard question last exam. So we'll spend some time discussing that one. And then back to problem number 1, just a rough selection of doing particular limits like this. So it looks like altogether about 10 to 12 questions is the expectation. Other questions at the moment? Okay, I should probably go back to the current semester before I forget. Okay, so at the next week when we return, essentially all we're going to be doing is look into reviewing some final exams, those kinds of things. But just like any of our exam reviews, a week away from today on Thursday, if there's questions you'd like to bring to class, then that's a great way to do the review. So I'll start by taking student questions. If we run out, I'll have lots of material, again, posted right around here that we can start looking into. I might modify some of those real exams given the last semester to match up the problems that we actually are going to work on. So less questions that won't be asked, more of the actual questions we focused on this semester. So that takes us now back to section 5.3. And that 5.3 section, here's where we left off, right before going on to the weekend, kind of a rough diagram. Let's look at this just really carefully for just a moment to get our orientation straight on this. The idea is we grabbed a function. That's the blue curve, y equals f of x. And what we want to determine is, what is the signed area under the curve? By signed area, what we mean is from here to here in this region, this area is going to be considered positive because it lies above the x-axis. Then when we go to the other region down here, the curve y equals f of x is below the x-axis. So this area here would be negative altogether. When we go to integrate, we're taking the exact positive area, taking the exact negative area, subtracting them, and really all it is a new kind of limit. This is the n equals 4 diagram, but we want n to go off to infinity, much like when we're calculating, say, a derivative. We take a limit like this, but h goes to 0. It's a different kind of setup. N is the number of rectangles that we see here. And so as the number of rectangles goes higher and higher, here's the 4 diagram, the area itself becomes more and more accurate. And if this limit exists, we define it to be the exact sign area of this curve. But other problems we've encountered in chapter 2 is that this limit doesn't always exist. It can fail. So we need a little bit of extra information to ensure it must exist. Let's go back to section 4.2. Actually, let's go back even further. Section 4.1 actually gave us the right conditions for this area to exist, because in that particular section, we go all the way down to the bottom here and look into the closed interval method, or maybe a little bit further, the extreme value theorem. This theorem was really, really pivotal in calculus. Not as important as it seems at first, but now it's a big deal if you're looking for areas. It says if you have a continuous function, so that's one ingredient we really want, continuity, for that area to exist. And if it's continuous on a closed interval, that's the second ingredient we want, then there will be an absolute minimum and an absolute maximum. So if there's an absolute minimum and an absolute maximum, there is going to be a finite area. There's the absolute max, there's the absolute min, and this limit, we'll find that exact area. So that's the idea together. So the next thing we look into is we don't necessarily want to compute that limit, or just like how when we compute derivatives, we don't necessarily want to take that limit every single time. That's working really, really hard. So we need a good theorem that's going to support how to compute this limit in a more reasonable way. So the first thing we do is we change up the notation. So this symbol right here is referring to a definite integral of the function f of x from bounds a to b. The a to b are the same values we see here, a and b. So we integrate, is what we say, from a to b, the function f of x. But this is all just notation for what we mean over here on the right-hand side. The limit as n goes to infinity, as I goes from 1 to n, of that summation. So this is just counting up the areas of those rectangles. And now this is a new way to just represent that limit. A lot of interesting language goes into here. We call this entire thing on the right, this part, let me try to target that better. This part is referred to as the Riemann sum, named after the German mathematician Bernhard Riemann that did a lot of this kind of work way back in the day. So this is not the most modern mathematics, but certainly looks sophisticated. There's lots going on. We call that little symbol, it's supposed to be an elongated S really. And the S is referring to the summation right there. So the notation is meant to remind us what we're really doing. We're taking a sum. Sure, it's an infinite sum, but that's what this is denoting. So we elongate that S, just write it out this way. And we call that the integral sign, usually written about like that. So that's the first portion. We have an integral sign. Then we have to have bounds on the integral sign to say, where are we collecting the area under? We'll refer to A as the lower limit, B as the upper limit. And the thing inside has kind of a funny name. If we're integrating, we call this the integrand. A lot of vocabulary out of nowhere, but not vocabulary you have to strictly memorize, more just recognize when you hear it said. So the limits of integration is where you find the area. The integrand is the curve you're finding the area under. And dx is much like writing, say, f prime of x is the same as d by dx of the function f of x. It's telling us the variable upon which we're integrating. Just like over here, f prime is kind of mysterious, but if we say d by dx in Leibniz notation, we're saying we're differentiating and x is the independent variable. So dx here reminds us of the independent variable, but it's just kind of an artifact from delta x. Delta x just gets swapped out as a dx as just a new way to notate the independent variable. Well, putting that all together, we have the Riemann sum. When you put a limit in front of it, we say we're taking the limit of a Riemann sum. And finally, theorem 3 tells us when the limit will exist, therefore the integral on the left exists as well, we want continuity, like we mentioned on the extreme value theorem, on a closed interval. That alone is going to tell us this limit is guaranteed to come out as a finite number. Or there's some things you can do to generalize this. If it has a finite number of jump discontinuities, then that would work as well. This is a statement that doesn't really come into play a lot in this course, but it's something to just be aware of. You can weaken this just a little bit as long as it's specifically jump discontinuities. and not infinitely many of them. If there's infinitely many jump discontinuities, we have a very complex function indeed. So that's it. We just wanted continuity on a closed interval. When that happens, the integral on the left exists, which tells us the limit comes out as a finite number. There's a weakness to theorem 3, though. Theorem 3 doesn't tell you how to compute this. It just tells you when the limit will have an answer. So we're looking for continuity. And finally, the way we compute is going to be referred to as the fundamental theorem of calculus, confusingly part 2. There's actually 2 portions. We're looking at the evaluation theorem of finding the area. Before we check out that theorem, any questions at the moment? Okay, so here's how it goes. Keeping your last quiz in mind, that's what the role of antiderivatives was all about. And we kind of hinted at this as well on the last classes. Fundamental theorem of calculus part 2 says, again, we want continuity on a closed interval. We take our f of x over here, then form an antiderivative, uppercase F, where f is any antiderivative whatsoever. The word any is kind of nice here. When we were finding antiderivatives on the quiz and the last section, we often wrote plus c to make it the most general antiderivative possible. But when it says any antiderivative, it means we'll take c equals 0. We don't need the constant of integration if we're evaluating this through the fundamental theorem. But if you did leave c inside there, that's okay, because it would subtract away through this equation here. You would have an antiderivative plus c minus another antiderivative plus c in a group, and c would just cancel out. So we might as well just take it to be 0 when we find that antiderivative. In Leibniz notation, it looks like this, same kind of idea, d by dx of f of x. That's the lowercase function f of x. And if you take the derivative off, you're looking at the antiderivative. Kind of a more confusing way to express it, but same kind of information. So again, this is really pretty wild. It's telling us this function, which is defined on all numbers from a to b, we can find its exact area just by taking the difference of the antiderivative purely on the boundary, a and b. Very strange theorem altogether. As we go to analyze this, we'll also visualize what we're computing just to make heads or tails of how do we compute an area out of these things here. We'll start off by just plotting this. The function is integrand f of x, 2x plus 5 over 3x. Looks like it's a pretty complicated function, but we have a restricted domain. Lower limit is -2. So we'll take our domain to go from -2 up to the upper limit, -1. And that's our curve right there. Just a tiny little curve below. When we go to integrate, what we're finding is this. From here to here is a bound from the lower limit of -2 to the upper limit of -1 right around here. The horizontal axis also causes a bound. And this is the area we're going to get. It's really helpful to have a diagram like that because it's going to tell you, does your answer even make sense? If we integrate and get a positive area, we're way, way off track. And because that's such a big help, when I go to write the final exam, I'm going to include a graph like this. Not the drawings you'd have to add, the drawings like the bars, the negative area, but you'll have a little bit extra information on the problem to kind of guide your answer to see if it's correct or not. So here's what we're expecting. I'll leave it down below and clear that out. Now we're going to give it a try. Let's grab the theorem up here as well as we go to compute. Maybe the first thing we should do is let's re-express this function in a more reasonable way. An antiderivative of 2x is not too bad. That one's just an x squared. But the antiderivative of 5 over 3x, that one's actually kind of confusing just because of the way it's been expressed algebraically. So my first step is clean that up. We're integrating from -2 to -1. 2x plus 5 times. Let's make it 5/3 times 1 over x. So this is the function we want an antiderivative of. This is the lowercase f of x. I'm using the same exact notation essentially with that lowercase f of x that we used in section 4.8. What we need now is an antiderivative of that. Let me cap this off with the dx. So now finding the antiderivative, it'll look like this. Let's write it in blue to emphasize it's the antiderivative f we're producing. Term by term on this one, just an x squared. And the process in section 4.8 is, once you get one piece, imagine differentiating it. Sure enough, the derivative with respect to x of x squared is a 2x, so our first term is correct. The next portion, we're going to use a constant multiple rule. It's 5/3 times 1 over x, so we'll go plus 5/3 times. This is the confusing one. This is the reason why we separated it out as a 1 over x. Anyone recall the formula for antiderivative of a 1 over x? Yeah. Good call, absolutely. So that one, that's the only reason we separate out that 1 over x, just to see that pattern. Natural log absolute value of x, just as you said. Let's use that little notation there to indicate it. Yeah. Only if there was a plus in the middle. Because of the multiplication right here, when we go to differentiate this part, d by dx, we keep the 5/3 through the constant multiple rule with differentiating, and then the derivative of the natural log x would give us back 1 over x. But yeah, absolutely. If we had a plus in the middle, we'd have to attach an x to it. Other questions at the moment? Okay, we've got an antiderivative. And in section 4.8, if you're thinking, put in a plus c, good call on you on thinking that. That's the right thought, except here, if we're using the fundamental theorem, any antiderivative does the job. We take the simplest one. So there's no need to put a plus c here. If you did, it would just cancel out. It wouldn't cause any harm otherwise. This is where the notation gets a little bit interesting. Notice it says f of b minus f of a. We wrote f of x right here. It's the antiderivative. So one extra bit of notation that's not actually expressed here when the author goes to use this, but you'll see it written out on the examples, goes this way. We're going to evaluate from -2 to -1, and this bracket is an evaluation bar. Some people write their bracket more like this. That does just fine. Other times a bracket's written kind of like a half a closed interval type of a bracket, and its whole purpose is kind of like when you go dy dx, evaluate at x equals some kind of value. It's just a way to say, evaluate the result on the left on these specific values. So this is the weird looking notation step. After we get the antiderivative, we don't necessarily want to write out f of x equals all that stuff and then go f of b minus f of a. Instead, we write it out this way. We take x squared, plug in -1. So -1 squared plus 5/3 times natural log absolute value, plug in -1 there. So in this theorem, when it says f of b, the b value is the upper limit of integration, and that's this -1 value. This whole portion right here is f at b equals f at -1. So we evaluate whatever this is at the upper limit first. Same as what's been said down here. Then we go minus. We need a parenthesis because of the two terms for the antiderivative. And we just do another evaluation. This says f of a. A is the lower limit of integration. For us, it's a -2. We copy it down here just for extra clarity, so we're not looking up if we had a lot of steps. And now, go back to the function, the antiderivative. We're just plugging in a -2 this time. So it's going to be -2 squared, 5/3 times natural log, absolute value, -2. So this portion is f of a, which is f at -2. This is kind of hard to track on the first time we're seeing this, so we're going a little bit slow to show where things are going. This part right here is the right part of the theorem, but in practice, this is how the work on the results written out by hand really looks like. We just write down the antiderivative, bracket to say what the b and the a value is. And when we go to evaluate it this way, don't forget the minus in the middle right here also drops to that part, causing also a need for 2 parentheses. But then we have f of b, f of a. All we need to do is just simplify this big result. And this is going to be negative area, so we're going to check that if that really tracks as well. Any questions so far, folks, to this stage? Okay, at this point, the calculus is done. It's all arithmetic from here on out, so let's carefully compute these things out. If this was a real final exam, if you made a mistake here, I'm going to chalk that up to just a simple arithmetic mistake, maybe nerves on the exam. This is where the calculus really ended. If that's right on paper, you're potentially just getting full credit right at that step. We do have to calculate this, and that's going to be a check as well if we get a negative sign. So let's keep pushing forward. That's a positive 1 plus 5/3 times natural log, a positive 1 as well because of the absolute value. This is just a fancy way to say 0, but we're putting it in for clarity. Then on this next part, it's going to be minus 4 plus 5/3. Natural log, absolute value of -2 is a positive 2. So just like on the other one, let's throw a positive 2 there. Cancellation from here because natural log 1 is 0. And now it becomes 1. Distribution happens over here, minus 4, minus 5/3, natural log 2. So our signed area is -3 minus 5/3, natural log 2. That's certainly a negative number, so that's pretty comforting. We do get negative. Let's see the magnitude of that number. -3 minus 5/3, natural log 2. So it's about -4. Now let's see if that makes sense. The average height of this is at about -4, and the distance, the width, is from -2 to -1. If it looked exactly like a rectangle like this, instead of the red curve, that area is exactly -4. So our slightly more refined answer is extremely close in the right ballpark. We get that extra bit and that extra bit to cancel out, getting the exact area figure there. So that's what the fundamental theorem does for us. It allows us to do an exceedingly complicated limit. If you're curious on the reading, the author does show some of these limits computed, but we're going to directly compute them through the fundamental theorem like we did in this result here. This is called the fundamental theorem of calculus because what it's really done is it's found a way to tie differentiation through the antiderivative together with a whole separate problem, finding the area under a curve. Differentiation was just trying to find a slope of a tangent line. So these seem like totally different problems, but independently, both Leibniz in Germany and Newton in Britain discovered this fact. There's a tie into the area problem and the tangent problem. In a real sense, they're the same. One is just the inverse problem to the other, and it was a huge surprising fact. That's the only reason it's called the fundamental theorem. And again, this is just the second part. There's other facts tied together with it. Our goal today is just to practice more with this technique, is tying in together what we did with finding the antiderivatives. And if we run out of time, I'm still going to solve these last problems, particularly these application problems down on the bottom. I think this would be a tough extra credit kind of problem, so I might give another different kind of extra credit problem as well for a couple opportunities on the exam. Something along the lines of these, or maybe just another version of one of these as well that's just slightly more built up. Because this is the last topic of the entire course, the problems I'm going to ask are to be a little bit more routine when they do show up on the final exam, since I realize limited opportunity to study this kind of topic. But our goal is to study some more, so let's move over to part B. Any questions whatsoever first? Okay, so all of this is about finding that antiderivative, just like you were working on the quiz in section 4.8. So here's our next try at it. Still pretty new technique, so let's carry in this from the next problem as well. And one thing that's kind of causes a big drama in calculus is finding out when you have a constant versus when it's non-constant, a function that varies. Same kind of issues come up in calculus. In integration. That's a constant function. So if we were to visualize what this problem is all about, here's the visualization on this one. Let's plot natural log 5. There's no x there, so when we go to write f of x equals natural log 5, it's on there somewhere. There's a curve on there. Once I get that typed in correctly. And there it is. It's just a constant flat curve. So we want the area under this curve. The area is infinite, right? But if you put in bounds on the integration, you do get a finite area. So let's put in the lower limit 4 for the lower bound. Upper limit 9 is the upper bound of integration. And now we have to move over here to get to the right bounds. All we want is the area under that curve. Our job is essentially done, right? The height of this curve is natural log 5, approximately 1.6. The width of the interval is, well, 5 units. So you're just finding the area of a rectangle right here. 5 times natural log 5 should be the answer. But just because it's a basic problem like that, doesn't mean this isn't still an interesting process. If you knew this is just a constant function and you wrote down on paper in an exam, 5 natural log 5, I would say that's terrific. I would interpret that as you found that that's just a constant. Area under a constant is just the function times the width of the interval from 4 to 9. So that absolutely qualifies as an answer. But let's give another answer. Maybe let's call this, just for clarity on the notes, method 1. And method 1 was all about using the fact our integrand we're putting in as green. So let's write it this way. F of x equals natural log 5 is a constant. So we've got the exact area there. Let's actually add the Desmos graph just for a little extra emphasis on that. If we were differentiating natural log 5, that would have just been a 0. And now if we're integrating it from 4 to 9, it's just this area right under the curve. So 5 natural log 5. Well, let's suppose we really did use the fundamental theorem, though, and see what happens. That's actually pretty much just as fast. So this is one where you can go either way. You get the right answer. Notice first it says dy, so there's a different variable there. It could be any variable. It could have been, say, z. It could have been u, x. Let's keep it a dy just for emphasis. The antiderivative of this one, because we have a constant back in section 4.8, the trick is what you put down is the constant times x, and that totally does the job, except I made a mistake there. It's not x, is it? It's a y variable, so we should say a constant times y instead. So we've got the right antiderivative. We evaluate this from 4 to 9, and it'll turn into this. Natural log 5 times, plug in a 9 for the first part, and that's the f of b portion, which is then equal to f at 9. Then go minus. These minuses are sometimes hard to track, so I'm going to highlight them as we go. Minus natural log 5 times. Now we're plugging in 4 for y, so just a times 4. But these are now like terms. Natural log 9 copies of natural log 5 minus 4 copies of natural log 5. Give us all together 5 natural log 5 for the total answer on that one. And the upper limit here was f of a, which is f of 4. So either way we take a look at it, we get 5 natural log 5. The purpose of this problem is those constants functions like natural log 5 are tricky sometimes. But it's also a way to say The fundamental theorem is giving us exactly what our intuition would have said. We decide to just analyze this purely geometrically as a rectangle. So that's a good comfort. We're matching up the same values either way we look at it. Well, that's our second one down. Any questions so far, folks? Yeah. Yeah, absolutely. If you spot the constant, this is the best answer, in my opinion, in an exam setting. You mean like put in a calculator, that kind of thing? Oh, yeah, the exact value would be just fine. If you did put in a calculator, that wouldn't hurt either, but this would be an okay stopping point. You know, actually putting in the calculator could be a good idea if you're, say, looking if this value is reasonable based versus anything that's posted on the exam as well, but it would only be optional. Other questions at the moment? Okay, let's get into the next questions then. These are the questions where algebra just starts to enter into the picture. Same kind of problems happen in sections like 3.3, the derivative, same kind of issue in section 4.8 on antiderivatives. Sometimes the format of how the functions are given are just not convenient. Finding the antiderivative of x cubed divided by the antiderivative of 5x minus 1 doesn't give us the right function. First thing we should really do is take the integrand, this function, and just simplify it. So let's rewrite f of x, 5x minus 1 squared over x cubed. If we were differentiating f of x, these steps would probably be the fastest way to differentiate it as well. Rewrite the expansion of the numerator, 5x minus 1 squared, using the FOIL method would give us 25x squared minus 10x plus 1 divided by x cubed. But that just means we're dividing all three terms in the numerator by x cubed. I'm going to rewrite it just to show that, emphasize. 25x squared divided by x cubed minus 10x over x cubed plus 1 over x cubed. So we've expanded the numerator. We've divided all terms in the numerator by x cubed. Now we start to simplify. This is the dangerous term, because when you simplify x squared over x cubed, you get 25 over x. So we might want to reformat that one, just to emphasize a natural log is coming into play there. On this one, this is going to be negative 10, x power negative 2. So really it's negative 10 divided by x squared, but I brought that up into the numerator because it's easier to use the reversal of the power rule or the power rule in its ordinary form if you keep the base up above. Likewise, let's change the base on this one and write it as plus x power negative 3. So that's a cleaner way to express our integrand f of x over here for the purpose of integrating. Next step, let's rewrite our integral as integrating from 1 to 2. This 25 over x, if it doesn't cause any harm, you can integrate just fine on that. But for me, I probably would want to write it this way, 25 times 1 over x, just so I don't miss that natural logarithm coming in play for that one. Then minus 10 x power negative 2 plus x power negative 3 dx. So the original question is just not algebraically helpful. Doing a bit of algebra on the right, this is a much faster problem to run right through. Here's what the next step is going to look like. We need the antiderivative f of x. Going left to right, first term is going to be 25 natural log of absolute value of x. That's tricky enough to still keep on pointing out to that one weird pattern break on the power rule. 1 over x just does not work in antiderivatives. We get the natural logarithm. But every power of x does work in the way we'd expect. Let's go carefully with these next ones. We have a constant negative 10 multiplying, so start off by writing in negative 10. Over here, we are going to use the power rule in reverse. Now, if we differentiate, the power would go down. So in the antiderivative, power goes up 1. Add 1 to negative 2. New power is negative 1. And then go over here and immediately divide by that new power. Doesn't hurt to highlight that just to emphasize that those next steps. So it's been a while since section 4.8. These were the major things we were doing, finding antiderivatives of these kind of functions. Does that look right to folks so far, to that step? Okay, then kind of just rinse and repeat on the next one. It starts off as something positive. Power is -3, so it goes up 1. New power is -2. I'll divide this way this time. We have to divide by that new power, so -2 on the bottom. That's the f of x function, and the fundamental theorem says evaluate it from lower limit 1 to upper limit 2. So just for emphasis, here is f of x. And it looks like a lot of stuff to compute here, so let's see what we get. Start with a 2. We have 25. Natural log. We're plugging in just positive values, so if you wanted to, you can drop the absolute value and just use ordinary parentheses. But it wouldn't be any harm if you left it absolute value 2. It's still correct, no big deal. I'm going to write it in this way just because we have positive values. Then on this one, this is a +10. X power -1 is going to give us a 2 to the power -1. We'll have to do a little bit of algebra on that. That makes it a 10 divided by 2. This is just a 5 we're looking into. Final one is plus 2 power -2 divided by -2. Put in a big minus sign, and then we do it all over again because this part was f of b, which was f at +2. The next part over here is going to be f of a, which is f at +1. So now we're just taking all this stuff, plugging in a 1. Gives us a nice simplification there, 25 natural log 1 minus, well, for plugging in a 1, this is just going to be +10. 1 to a power is still just 1, so no change on that. This one is 1 to power -2. That's just a 1 as well. So this whole term is just a -1/2. Got a little crazy there with the parenthesis. Let's shorten that up. So we have f of 2 coming from that 2 minus f of 1 coming from the 1 down below. If you're doing this as a problem on the real final exam, and this is accurate, again, that would be considered full credit. We're at that step. But for the sake of seeing how close we are to getting the right area, let's keep moving forward. We have 25 natural log 2. Let's work on the exponent on this one carefully. This is times 10 divided by 2 to the power +1 if we switch to the denominator. And this one is -1 over -2 times, because that power is -2, 2 comes down with a positive power squared like that. And let's collect our free cancellation there. 25 natural log 1 is gone. And it's just going to be -10 plus 1/2. So we're just about there. Let's run through the last portions of 25 natural log 2 plus 5. Double negation right here is going to give us plus 2 times 2 times 2 is 1/8 minus 10 plus 1/2. Problem gets kind of annoying right here because now we're looking into fractions. So let's do some fraction arithmetic on this. Let's go for a common denominator of, well, maybe let's combine some like terms first. 25 natural log 2. 5 minus 10 is going to give us a -5 plus 1/8 plus 1/2. We don't like fractions that one combined like terms gives us fewer fractions. Now let's do this next step. Let's pick a color here. 8 denominator there is going to give us 5 by 8, so 40 in the numerator. 8 as a denominator here is going to give us 4 in the numerator above. So 8 goes into 40, -5 times, -40, -5 times. 4/8 reduces to 1/2, so we do have the right quantity. And now it's 25 natural log 2. And let's see here, -40, -39, and then looks like -35 eighths altogether. The claim is that's the exact area under this curve from the problem. Let's double check maybe one last one on here to see if we have the right area. But any questions on the process itself? Okay, tough part about doing these kind of problems is figuring out exactly what in the world did we actually calculate. So let's do that extra work just to kind of pull the results together here. Our function was this one. Sure, we did some algebra and separate out like this, but maybe we made a mistake right there. Let's plot that one where it got compactified into just one fraction, f of x equals 5x minus 1 squared division by x cubed. So we definitely have a function on the right, but we need a domain from the lower limit of integration to the upper limit of integration, so from 1 to 2. Looks like we're in the wrong range for that, but there's the function. It's above the x-axis, so we're expecting positive area on this one. Let's see if I can get a better zoom in on that. And this is the area that we calculated. A little concerning with the negative 35/8. This is negative, we have a problem, but the factor 25 is substantial, so let's see what happens. 25 natural log 2 is a 17 minus 35/8 gives us, yeah, a positive quantity about 13. This had a width of 1, and the height is close to 16. The average height is around 13, so that absolutely looks plausible. This seems to be the exact area under that curve in purple. So let's throw that in as a screenshot. Again, our real final exam, I'll throw some of these graphs on these integration problems as well, just so that you have extra opportunity to check your work to see if the answer is reasonable. So there's that extra screenshot as well. And in a nutshell, this is pretty much what the problems are going to look like on the real final exam. What we're doing on the next part of the notes is just getting a little bit of extra practice on this technique, getting into some application problems if we have time. Any questions or comments at all, folks, with this one so far for that check? Okay, so integration is pretty weird, and it's kind of amazing how, if you step back from all this, the actual process, mathematically and legitimately, is these problems, where you break up the interval of the curve, put in approximating rectangles, calculate the area of those rectangles, and then take a limit as the number of those rectangles goes off to infinity. That's exactly what we're doing, but we're doing it in a really, really nice way through the evaluation theorem. And that's the purpose of a really good theorem. It gives you a way to compute something that is almost unapproachable doing by hand in an almost instant kind of way. So we used infinitely many rectangles to approximate the area under this curve. And the process through the fundamental theorem says it has to be exactly that. So let's try a few more just to see what's going on with the next ones. Part D looks like it's a kind of a tricky problem that deals with radical notation, cube root of x, fourth root of x. So like a lot of these problems, the first job is fix the function. A lot of the things we have to do is just work on exponents. You'll notice we've done a lot of exponent work throughout this course. So with that in mind, we're just going to do a little bit more. F of x is x times the group. The exponent work on this is a cube root is really just x to the power 1/3. And likewise, a fourth root is really just x to the power of 1/4. Next, if we distribute x through, we'll have x times x power 1/3 plus x times x power 1/4. On this step, we now have the opportunity to change the exponent on x. The exponent is originally a 1, but to match up with this, we should call it 3/3 on the first exponent. To match up that denominator, the other x should be to power 4/4. Then we just add those together. So on the next one, or next line, we have x to the power 4/3, adding up the exponents. At the next line or next term, add up the exponents on there, and you get x to power 5/4. That's, in my opinion, the trickiest part of the problem, just doing all of that exponent work. Any questions at all, folks, on getting those values? Okay, so the original function, just like a lot of things in calculus, this wasn't well suited to integrate at all. If you have x times anything else, well, in differentiating, that would have been a product rule, right? Integration, we call that integrating by parts, and it's more involved in the product rule itself. The only way to get out of all that extra complication is expand the function, because the antiderivative of x times the antiderivative of that group is not the right answer, unfortunately. But now we have a better problem. Integrate from 0 to 1, x power 4/3, plus x power 5/4. Dx tells us x is the independent variable. And now this is back to a section 4.8 type problem. This is the lowercase f function. We're producing an uppercase f of x function in that same exact notation in that last section. So here, antiderivative is going to start by writing in x, but put a little space to the left. Adding 1 this time is adding 3/3. So that becomes a 7/3 altogether. We have to divide by 7/3, but we discussed the most efficient way to divide is just multiply by the reciprocal. Saves us a line for sure. And it looks a lot less abstract if we just go on that route. The antiderivative is the new process, so lean on the fact that we've done loads of derivatives. Differentiate it right here, maybe on the margin or exam, maybe just on your mental chalkboard, as some people say. If I differentiate that, 7/3 comes down. It's just going to cancel right off the 3/7. And then we would subtract 3/3, getting us back to the 4/3 that we're intending. That quick mental check gives you a lot of accuracy in doing that kind of problem. And now we just do it all over again. Go plus, include a little bit of extra space. It's x to the power, add 4/4 to 5/4. We get 9/4. Now take the reciprocal, 4/9, and multiply. And that's our f of x function. Let me retarget this arrow. F of x in the fundamental theorem has to be evaluated from a lower limit of 0 to an upper limit of 1. So now we're just running through the evaluation of this. And this one's not so bad. One of the things that we'll spot and really kind of like when we see it is oftentimes a lower limit of 0 is just a kind of a freebie almost. Because when we plug in 0 here and here, everything is wiped out. The total value is 0 itself. Let's write it in just to show the process, the pattern of doing it. We start with a 1 and write in 3/7, 1 to power 7/3. That's just a 1. Plus 4/9, 1 to power 9/4. It's kind of nice that 1 to any power is just a 1, so it really resolves these complicated exponents. There's a minus in the fundamental theorem, still deserves highlighting because it's easy to miss that. And we do need parentheses as well, because we have 2 terms on this one. The negative sign has to distribute through. Except 0 killed it all off, right? We're just being careful with what it would look like in an ordinary problem. Plug 0 here, and it's 3/7 times 0 to the power 7/3. I'm just going to leave that as a 0. 0 to any power, still 0 itself. Except 0 power 0 is undefined. That's the weird one. Then plus 4/9 times 0. All the stuff over here on the right is 0, so our work is done. This is on the left, the f of a, which is f of 1. On the right, oh, excuse me, that is f of b, and then minus f of a. Got to get that definitely right. But a was 0, so that's why we plugged in 0 over here. So last steps, we're just doing a bit of arithmetic at this stage. It became 3/7 plus 4/9. We can combine those. That'd be 3 times 9 plus 4 times 7, divide by 7 times 9. So in the numerator, it's a 27 plus a 28, divide by a 63, and that's going to be kind of late in the semester for tons of arithmetic. Let me just do the freebie. 27 plus 28 gives us a 55 in the numerator. Divide by 63. So we've got it, folks. The exact area under this curve, this is just a positive function now, gives us that positive area, exactly 55/63. One of the things that makes this a little bit more interesting as well is, we've kind of hinted at this before, an area like this could mean just about anything. It could be a distance. It could be, say, a rate of change of a chemical reaction, one application we're going to look into, or it could be the total amount of growth of a particular organism. That's another application we're looking into. Essentially anything that involves a function and an antiderivative. If there's a derivative on the table, the area is an interesting applied problem to take a look into. So that's the purpose of doing all these kind of area sort of problems. But let's try out another one, part E next. Any questions first at all with this one? This one looks like it's a nastier, challenging kind of question. So let's work this carefully. 3x squared is okay. But it's that 3 to the x that causes a little bit more of a challenge on this problem. We don't have to do anything extra algebraically. It's ready to go. Let's put a formula on the right, because this one right here is oftentimes a weird derivative to take. It's a weird antiderivative to take as well. So if we write f of x equals 3 power of x, let's put in a derivative formula as well. I mean, we're kind of reviewing for the final exam even on these notes. F prime at x is 3 to the power of x again, multiplied by natural log of 3. So generic exponential causes us to multiply by the natural logarithm of the base of the exponential to the 3 to the x each time we differentiate. And now we can say the antiderivative is f of x equals, antiderivative of 3 to the x is 3 to the x. This is a reversal formula, so instead of multiplying, we do the complete opposite thing. Divide by natural log 3. And we could check if we differentiate that, derivative of 3 to the x is 3 to the x natural log 3, divide by natural log 3, giving us the right cancellation. The derivative of f of x is just 3 to the x now. So that handles that nasty term right down there. Now we can go and find the full generic antiderivative and the area under that curve. 3x squared minus 3 to the x from 4 to 10. These are really large numbers, so let's see what we get out of this. First, the antiderivative of 3x squared is right away x cubed. Then go to your mental chalkboard, differentiate x cubed. That is a 3x squared, so we're on the right track. This is the nasty one to watch out for. And by the way, I forgot to mention this at the start of class. As I start to put in documents down here, as we get closer and closer to reviewing for the final exam next week, I'm also going to make my very first thing include the formula sheet for the final exam. So you'll be well informed what formulas are provided, what kind of things we have to memorize. I probably would provide the generic formula for this one because it just doesn't come up a lot, even in this class. So now antiderivative of this one, negative 3 to the x, divide by natural log 3, per the formula on the right in purple. We do an evaluation from 4 to 10. And that means we're essentially done at this step. Let's run through this. 10 gets inputted first. So we have 10 cubed minus 3 to the power 10. So really large numbers are coming up. Divide by natural log 3. Then go minus. This left part is f at 10, where that's the antiderivative of f of x. Now we do minus f at 4. So this will be 4 cubed. That's just a 64, getting a little bit more tame. minus 3 power 4 is just an 81 over natural log 3. Kind of hard to know how much algebra or arithmetic we would want to do on this one, but there is some decent simplification, so let's keep on going. 10 cubed is 1,000. Over here, you might want to make a judgment call. 3 to the power 10 is a gigantic number. If you wanted to, there's no harm in putting in 3 power 10 like this, 59,049. But you know, in my opinion, that's a more simplified form of the same exact value. Again, it's a judgment call. If you left it in that form because of the high order of magnitude, I think that would be appropriate. But throwing in that number is just fine as well. So I'm going to leave it just as a power of 3. 3 power 10 is quite large. That's a much more simplified form to have on paper if we're looking at a value like that. Now distribute the sign through. 4 cubed is 64, so it's negative 64. This sign flips to positive. 3 power 4 is 81 over natural log 3. So there's our result. Not a huge simplification, but there are two pairs of like terms. First, we can take 1,000 minus the 64. Let me try again. For 936 on the first terms, here and here. Then, because the natural log 3 appears here and here, we can combine them to say plus natural log 3, take the 81 from over here, minus, do the negative sign over here, 3 to the power 10. In my opinion, this is kind of a nicer way to leave the answer. But if you want to do any further computation, that would have been just fine as well. Notice it's, let's see, I'm starting to get curious on this one. Do we have a negative or a positive value might be our question on this. Let's maybe investigate this a little bit further just to see if we are on the right track. I'm going to jump the whole number right into Desmos. 936 minus 81 minus 3 power 10 over natural log 3 gives us, yeah, a positive number. But is the curve positive? We're doing 3x squared minus 3 power of x on domain 4 to 10. That's an exponential function, so it has a high growth rate. So let's look into the function next. This would be provided on the exam, so if we have the wrong value here, if it's really negative, we'll know right away we made a mistake somewhere in the process. So f of x is 3x squared minus 3 power x. And this is on the domain, lower limit 4, up to the upper limit 10. And now the curve has disappeared. Let's go hunting for it. From 4 to 10, my hope is it's above. No, this one's below. So we have a negative curve on this one, but yet a positive number. That suggests there's a mistake somewhere.
I think it's 936 minus.
Oh, I gotcha. That's a silly mistake right there. And that's the worst thing that could ever happen on an exam, right? You might have the writing problem on paper, but on the check, it's in the calculator wrong. Darn it. Maybe a good test taking strategy for that is if there's a mismatch with what you're expecting to see, double check your calculator first before changing anything on paper. I think that's a good advice. Should have been plus, and now we get a large negative number. Makes sense. Our curve is really, really steep and slope below the x-axis. We're expecting negative. Okay, so at that point, I would be convinced we've got the right value on that one. That's the value of having a graph on the exam. So again, when I provide the integral problem, to the right is going to be a graph of the actual curve itself. Well, any questions at all, folks, surviving that one there? Okay, let's try this out again. This one is kind of a tricky question in its own right, but it goes on together with what we were saying in spirit, that integration and differentiation is in a real sense an inverse process from one to another. And look what we have here. We're integrating from 1 to 5, the derivative of some function. The way we would analyze this one is, if there's a derivative here, then this is a way shorter problem than you might expect. The antiderivative is immediately the root x squared minus 1 without the dx in front of it. So root x squared minus 1 would go here. And then we would just have to evaluate that from 1 to 5. That just doesn't seem quite right because all the other problems we did had a lot of extra effort and baked into it. So hold that thought for the moment. I'm going to do some scrolling through here. What this was really in spirit is Leibniz's form for the fundamental theorem of calculus, part 2. That's just expressed in Leibniz notation. So let's cite that right in the problem to clarify. So this is the fundamental theorem. In Leibniz notation. And it says, if you integrate a derivative of a function, you just restore the function itself. And that's exactly what we did. The function uppercase f of x was root x squared minus 1. So we just directly put it in the right here. I like the Leibniz notation version of this theorem because, again, it's emphasizing integration and differentiation are essentially an inverse process. In a certain sense, they cancel out. So over here, they cancel out, but you do evaluate from 1 to 5. So last steps on this one is just plug in root 5 squared minus 1, go minus. We don't need a parenthesis this time because just one term in the antiderivative. Plug a 1 right there. 1 squared minus 1. On the first root, it's 25 minus 1, so square root 24. On the second one, that looks like a 12. Let me fix that. On the second one, it was 1 squared minus 1, so that's just the square root of 0. That means our work is done. If you gave me root 24, totally fine with that. But if you went this route, I'd assume that you're just really took the algebraic technique of simplifying roots to heart. That's not a bad step to take. This could also be expressed as 2 root 6. Sometimes I do that in my answer key, but I would accept a root 24 as well if you left in that form. So that's how the fundamental theorem in Leibniz form looks. It's pretty odd at first, but then gives you a direct answer once we run through it. Any questions at all, folks, with running through this problem? Okay, notice the danger on this one, though. If you did this in an exam setting, and you weren't thinking in terms of that cancellation, which is what Leibniz notation is trying to express, you might have done it this way. Let's say here, not recommended. This is just for emphasis on what not to do. Maybe you might not even want to put this on your notes, unless you put in, don't do this on the exam as a quick reminder. You could have taken integral from 1 to 5, d by dx of, let's match up the notation, root x squared minus 1, dx, rewritten it as integral from 1 to 5. And if you're thinking in terms of order of operations, and you did differentiate that, we might be kind of stuck. I would give partial credit, though, because it's not a bad thought. Order of operations would say differentiate first. To differentiate that, you'd have to use the chain rule, and it comes out as 2. The root goes down below, x squared minus 1. We have to multiply into the numerator, the derivative of the input, x squared minus 1, which is a 2x, causes the 2's to cancel. But now this one is much harder than the original problem. Again, I would give some partial credit for that because we'd be essentially stuck at this point, and it wasn't a bad thought. But this is really essentially just a big trick question to know you can cancel there and move right through the problem immediately the moment you see a d by dx inside next to the integrand. Well, we did it, folks. That's the trick question part F. Any questions at the moment? Okay. Next topic is all about indefinite integrals. So let's clarify. When we write down something like this, integrate from a to b, f of x dx, the fact that there's limits of integration tells us that this is a definite integral and that the answer is a number representing area. So we call that the definite integral only because it has limits of integration. And then down below, we have a term called indefinite integrals. Notice there is no limit of integration whatsoever here, but all this really is a big notation change. In section 4.8, we didn't use this notation because we didn't want to define the integral before we even had the ability to compute it in the first place. So in the section 4.8 notation, we could change by just saying integrate f of x. It's an indefinite integral because there's no limits of integration, but all it gives us is the antiderivative f prime of x, solving f prime of x equals f of x. So that's just the general antiderivative of f. So written this way, the answer is not an area. The answer is not going to represent some kind of number like that. The answer is a function itself, f of x plus c. And we've looked into lots of indefinite integrals, really. This is how the formulas would have been stated in section 4.8. For example, this is the power rule that says antiderivative of x power of n comes into play in this way. Power goes up by 1. We divide by that new power n plus 1. And other weird antiderivatives are also collected here as well. But I'm thinking because we have like 4 minutes left to discuss this topic, I'm not going to include this kind of stuff on the actual real exam. I will have these formulas, but I'm going to keep them in the section 4.8 notation where we're just a lot more familiar. This is the part of the exam where there could be some extra credit questions, but I'm going to have an extra credit question along the lines of doing a kind of integral like this, but maybe a slightly trickier one. Part F would be a version of that. And another extra credit question that's along the lines of either one of these two equations down below. I'll post the solutions, so if you want to go beyond the course coverage and study those kind of problems, you'll have substantial extra credit on the actual final exam. But I think this is a good stopping point for us. There's maybe not the most value in pushing forward in 3 minutes on the last day for new content in the course. Any last questions at all then, folks, before we call it a day? Yeah.
And you said to just ignore that weird algebra question that was on the last year's exam.
Yeah.
You won't be
Not at all. I felt like that question was painful to assign, and people who saw that question on the final exam also left comments like, did we cover this? Stuff like that. I actually told them that department about that because it turned into almost a complaint on the exam over it. We do know what the question is this time. It's going to be something routine. It won't feel like something weird was baked into the exam. It's a standard question this time. Other questions at the moment? Okay, probably what I'll do when I go to post those real final exams is I'll post the real final exam and I'll say final exam fall 2024 version 2, where I switch out the problems into more reasonable actual problems, taking out the ones that are not actually going to be on our exam. That way we'll be able to target it a little bit better, but you'll still know what the original exam was at the same time. Well, any last questions at the moment? Okay, well, thank you for your hard work, everyone. It's always kind of an adventure getting to this point in a course like this. It feels like forever ago when we were talking about limits all the way back in, what was that, January. But if you have any questions while you're studying, I'm going to be pretty available from here on to Friday, the 9th of finals week when we have our exam. We'll talk more about the final exam next week. But take care, folks. I'll see you all next time. Yep, you betcha.